2017 level 3 mechanics speed run. Okay, let's go, guys. Let's go. Stop. Started. Okay, let's go. Let's go. Let's go. Alright, so here we know this is a translational question to us from now. Kelly just between Sam and the center of mass is Sylvia and her. So, 4 meters, 8 meters apart. This is an XCOM equation. So, is that XCOM equals? So we got M1. We'll do it. Wait, calculate the distance between Sam and the center of mass. So we'll do it from where Sam is 0. We got where is it? 1 point. Wait, no, 1 0. Oh. 05 times 0 plus 95 times. X2. Are they 4.8 meters apart? Or they not say? Oh yeah. Okay. Screw it, I know that's 200. XCOM. Let me grab this. Wait, this is the difference between Sylvia and math, I think. So we get 2.28 meters. 2.28 meters. That's when. That's the distance between. I actually don't know if that's Sam and center mass, but speedruns. Okay. Trouble happens at center mass. Astronauts move closer than collide. As the astronauts move closer, their would it be their velocity or their XCOM will decrease proportionally or at a constant, I think might be better. At a constant. Being 0 when they collide. I'll just state the speed as well. Velocity will be constant throughout. Okay, calculate astronauts' combined speed after they collide. High speed. How do we do speed again? Oh my days. Oh, P equals MV. Oh yeah, it's PI, PA. Okay. Combined speed. So we got PI. P and 9 initials. We got 105 times 1.2. That's for Sam. And then we got PI equals 95 times 1.4. PI equals PF. Okay, so now we know that. I'm just gonna chuck these in my calculator. Quickly do them. 126. This is KGMS. Ugh, I don't have much for that. That's my one. 95 times 1.4. 133 KEMS minus 1. Okay, so we got 126 plus 133 is equal to their combined mass, which is 200, which I said before. VF. So VF is equal to 26. That's 259 divided by 200. 1.295. This is 3SF, so we will do 1.30. Alright, next question. The spaceship is on the planet circular motion. Goes to orbit around the period of that height 351 above the surface. Kilometers doesn't matter, does it? Isn't it usually measured in I don't even know. Mass of the planet. So I'm just gonna use my trusty old equations. I'm just looking at what we've got. We've got time, which is kind of weird. I kind of forgot what time is helpful for. Might be for the next equation. Yeah, this is my weakest question. So we know FC equals mv squared divided by r. We know fg equals big G, big M, r squared. Oh, mass of the planet, actually, that's not too bad at all. So we're gonna make fc equal to fg, mv squared over r is equal to g m r squared, where m is a big planet, so m equal big planet. So we get v squared is equal to g m over r. We don't know velocity though, it's just kind of odd. Oh wait, did they give us some information? No. Radius, we know G. Don't know M, and we don't know. I seriously don't know what equation to even use here. Circular. I'm wasting my time, oh my days. Time actually could just be a kinematic, but you need a VIVF. That doesn't even make any sense for a kinematic. This question is weird. Okay, so what is something that could include time? That's what I'm gonna look for. Impulse? No. Frequency, yeah. Kinematic. Change in time? Angular? But it's circular, so you don't use it, I don't think. This might be the question that I skip real quick. Okay, I'm gonna skip this one now. On the journey, turn... Spaceship go faster for planets, spaceship path, turn... Okay, explain how spaceship speed changes as it gets closer to the planet. This is good, yep. As the spaceship gets closer to the planet, especially gets closer to the planet, it gets into its gravitational pull or field. I'll say field. Proportionally. To its displacement. I don't know. I'm just gonna use some big boy words here. Displacement to the thing, yeah. Okay, and then this results in FG to increase Fg equals G mm divided by r squared. As Fg increases, Fc must also increase. Fc is equal to mv squared divided by r. Thus, as radius, would it be radius decreasing? Well, yeah, radius would decrease. Thus, as radius decreases and mass of spaceship is constant, the velocity will resultingly increase. I really think I should be able to get this question. I don't know why I can't. Okay, so what do we know? Okay, this is when we're gonna use the F equals. We're gonna use that like one of those equations. We know radius. Radius will be 351 plus 5220 times 10 3. 351 plus 520. So we got 5571 E3. We got 5571000 meters. We know radius. We know G is just the gravitational constant, which is here 2.67. Let's go. Velocity. Okay. I think I know a way of solving velocity, actually. This is an equation which we're not given, which is sucks, but velocity is equal to 2 pi r, which is just the circumference. 2 pi r is circumference divided by time, because that's like the amount of time it takes to go around one rotation. And we're given time. Okay, this is, I can see why it's an excellent question then, actually. 2 pi 5571000. Okay, I probably should have left it in the other form. Divided by 5.46 times 10 3. Very important part here. Square. It's equal to 6.67 times 10. The negative 11. Negative 11. Negative 11. Times m divided by 5.4. No. Divided by 5571000. I'm just gonna chuck this on the calculator. I can't. Oh, I just took it out. 57100. We'll just convert that to alpha A. Okay. U shift I times alpha A divided by 5.4633. Square it. Times by 5571000. And divided by 6.67 e negative 11. Yeah, it looks like a pretty ordinary mass. We got 3.43 times 1024 kilograms. Alright, that's cool. How much time we got? 15 minutes? That's low-key kind of slow. Okay. A lot rotational here. I'm just not going to read any of that. Calculate the size of torque required for each rocket to cause an angular acceleration of 0.02 radian per second. Torque is equal to rotational inertia times angular acceleration. So we're given rotational inertia right up here. Okay, here's the thing. From each rocket, because calculate the size of torque required from each rocket. So that means we only have to use that once. We don't have to add them together. 5.8 E4 times 2E, 2E, negative 2. Okay, we got 11160. Torque is Newton meter, I think. But I don't know if they change it. Okay. Rotating clockwise at this many radians, that's velocity angular. Wait, what? Oh, so it does it once when the rockets are fired. Okay, so it's over time. Do they give us a time? We don't need a time, but do we? So we're given 0.58 is equal to distance, which is 2 pi. We're changing time. However, we don't know if that's changing. I think I know what I can. Okay, so we find change in time first. 2 pi over 0.58. 0 is pretty bad. Okay, 2 shift pi divided by 0.58. We get 10.83 seconds. That's super slow. I'm kind of doubting that. And then we use this equation. Changing omega over changing time. Spaceship is rotating. Calculate the angular speed of the spaceship. Okay, so this is where a trick comes in. Where I was talking about before. Angular acceleration. Wait, apart from each rocket with angular acceleration. Hold on a minute. Calculate the size of torque required from each rocket to cause an angular acceleration of 2. Okay, so this number will be half actually. One, because that's for both. 0 divided by 2, that's 580. 580 Newton meter from each. Okay, so we do have to use that this value from before. We get 2 times 10 negative 2 is equal to. Change in omega would be final minus initial, so we got omega final minus 0.58. So 2e negative 2 times 10.83 0.2166 equals to omega f minus 0.58. Okay. Wait, so it's accelerated. This is a bit sussy. I don't know if I find this question. So, final speed will be increased. That's sussy. I don't actually believe that. Also, why is it like that? Why is it like glitch when I'm like moving it up and down? I don't know what's happened there. Okay. Did I do it right? I think I did. It'll increase actually, probably, because when it's initial. What, do I have like a bowl with me or something? My earbuds. I just and they'll start increasing. Yep, obviously. Seeing why the torque used by the rockets is constant. Um, okay, so torque equal to I alpha rotational. Wait, they say angular momentum anywhere? Rotational inertia. It's gonna be angular momentum question. As angular momentum is gonna served. The system is in space, that's why. Rotational. Wait, oh, this is actually confusing. I don't think I use MVR. Mass decreases, so velocity increases. Hold on, maybe that's right actually. If when mass decreases, velocity increases. Increase. Thus, angular loss. Thus, omega will and its torque equals I alpha, and alpha equals change in omega over change in t. As I decreases and torque is constant, then angular acceleration must increase. I think that's a good enough answer. They always like the part 2 questions for this. Oh, yeah. Okay, this is like an angular momentum question again, I think. Do they give us rotational inertia increases, so I don't know if the last question was angular momentum then, but I'll keep it as angular momentum is conserved. in space. No net forces. As rotational inertia increases, the cells are extended out. The angular acceleration will decrease. Period of rotation, that's actually interesting. I would say, because I thought the velocity would change. Period of rotation. Oh yeah, I think I see what it is. Angular acceleration won't decrease angular velocity. Got that run wrong. And then look, we get this equation. Oh my god, that is not the right thing. What if I draw theta? There we go. So, in angular... I'm just going to explain this real quick. In angular momentum, or in angular physics, one rotation will just be 2 pi. You can't change the rotation for each period. Thus, as omega decreases, and change in theta in a period is constant, change in time must increase for a period of rotation. Boom. Okay. Calculate the period of rotation when the photovoltaic cells are fully extended. What info do we get? Sometimes they're rotating freely. Oh, okay. It's gonna be kind of annoying, actually. Rotating freely at... Okay, I'm just gonna go like this. We'll just find L. So we got before that the rotational inertia was 5.8 times 10⁴. It's 4, not -4, I don't think. And we'll times that by 0.45 to give us the initial, which is just angular momentum, which is conserved. 26100. Wait, this one will give you a tick as well. kg ms -1 per second, I think. Kilograms meters per second. Oh, I don't actually remember. Kilogram meters -2 -1, I think. No, I think it's -1 -2. I don't actually remember. Okay, this one's that. I don't know the equation for that, but oh well. 26100 divided by the new period of rotation, new rotational inertia. 2.74 times 10⁵. Okay, I must have gone the other one wrong. That means rotational inertia. Oh, increased by 2.74. Oh, okay. That's 2.74 plus the original 5.8 times 10, 4 is equal to omega. So omega is equal to 0.43 rad per second. That's not actually much of a change. Oh well. Okay, so we've got 0.43. I'm going to put it in that equation that we were talking about before. Delta time. Ugh, shit, I'm just going to get rid of the delta theta. Just know it's 2 pi. Thus, delta time is equal to 2 pi over 0.43. 2 pi divided by should answer 14.6 second. Boom. SHM question. Oh. Yes, we've got last question's damping, I think. What are we at? 31 minutes? What worst speedrun ever, bro? It's time, bro. Period of 8 seconds. I'm gonna do that. These are the only equations we'll need now. If she moves away from equilibrium in the positive, the restoring will negatively increase. As she moves in the as force equal to is proportional to negative y, and acceleration is negative y. The average of her oscillation is 1.12 meters. We use a reference circle or other methods. Calculate the shortest time it takes for Sylvia to move up 0.08 meters from her equilibrium position. I'm not really going to use a reference circle because I don't like it, but we know this is 0.12, and then this is going to be 0.08 meters. 0.12 plus 0.08. It's gonna put it in the calc just to be safe. Should just be 0.2 though. Yep. 0.2 meters. Okay, what am I gonna try and find? No period. Omega is equal to 2 pi f from up here. We're just trying to find displacement. Shortest time for her to move up. What? You're just trying to find the time. We're given time for a full period. Okay, I see why reference are confused. Okay, so we know 0.12 is gonna be... Wait, what? Oh my god, I actually got how it worked. Wait, so we got sine wave. This is max amplitude, and this is minimum amplitude. Okay, so yeah, this is 1/4. 0.12 is 0.12 meters is, I don't know if proportional is the right word to use here, but we'll go proportional to 2 seconds. So what's 0.08 divided by 2? .12 divided by 2. Might just ratio it. Actually, 0.12. Wait. Actually, no, this will work. 0.08 times 2. 0.8 times 2 divided by 0.12. 0.08 times 2 divided by 0.12. Doing 1.3. Okay, so the change in time will equal 1.33 seconds. Also, this is way larger. It's like that much. Thus, it will be 2 plus 1.333 equal to 3.33 seconds. Yep. Next is below. Graph still with velocity versus time, starting when she's on the closest to the floor. Closest to the floor, so we know velocity is at a max center, so velocity will be a sine graph then. Because, yeah. Velocity is a max here. V max. V min. Right? Yep. What's her max velocity is a good question we need to find out. So we know it's a sine graph. Velocity is equal to negative 0.12 times 2 pi divided by 8. Yeah, that's frequency. Sine 2 pi by 8. By 8. I actually don't know if this is correct. Shouldn't it be when time is 2? Hold on. Yeah, time should be 2 seconds here, actually. Oh, okay, I got it. So velocity will be equal to 0.94 per second. So at 2 seconds, it will actually decrease. Be a negative sine graph, right? I don't know. I'm still trusting. That. On. That. When she's closest to the floor, she'll be starting at this position. Alright, quick intermission. Back. So velocity wouldn't be at a negative max, would it? Well, yeah, it'd actually be moving away, so velocity would be negative max. Okay, I think I just probably should be fine. Oh, that's so hard to draw on this. Pretty bad. Okay. Start oscillation, vertical force, calculate Sylvia's mass. What? Okay. Force. Oh, okay. So we want to calculate her mass, which is... Oh, this is an interesting question. Actually, let me see if I can show everything. No. Oh, this should be good enough. I think it's an F equals ma, because we've got to find acceleration. Wait, no, okay, so we're given force and distance. Oh, okay. Spring constant, maybe? Yeah, I think spring constant is fine. 4.4 divided by 0.12 that equals K. 36.7 Newton meter minus 1. Okay. We know spring constant, now we need to find mass. I think we could probably use a time equation, right? Yeah. T equals 2 pi m divided by k. So we know... Isn't that for the period, though? Ah, it is. Oh, well, we'll just do it. I don't even know. M divided by 36.67. Okay, so 8 divided by 2 pi, that's equal to 1.27 square. We'll square it just so we get mass divided by 36.67, and we get mass is equal to square it times by 36.67. See, this is like a pretty standard mass, I would say. So I'm gonna be happy with it. Okay, I'm just gonna rewrite it. I wrote it really badly. Okay, describe any assumptions you made to simplify your calculation. Oh, shite. Okay, I assume that Sylvia is the only mass acting on the system. So 0 spring mass. And then is there any other assumption we can make? I think this is as good as we get. Okay, I think we can stop there. 45 minutes, 26 seconds. Pause. Alright, now we're gonna grade it. We're gonna grade it. Okay, give me a second. Give me a second. Okay, I'm back. Alright. So, I'm just gonna go all the way back up. What do we get? 2.28 meters? Boom. Merit right there. Merit tip. What was the next question? 0.92 meters per second? For the other? Wait, what? Oh, okay. Center mass keeps moving at a constant velocity, so that this question's correct. 0.92 meters per second. That's wrong. I'm actually surprised I got that wrong. What did I do wrong? Square root. Because it's, yeah. This is the part I forget. Total momentum be calculated correctly or correct method of mentioned the following error report. Yeah, so that's an achieved tick. Because this should be a square right here. I forgot about that, and these should be squared because these are at like right angles to one another. So it's like that. It's like that. And that's final. Because this is like PIS, PIS, This is PF total. That's why. I forgot about that. That's actually an error, but that's actually a good one to make right now. I'm actually happy I made it now, not later on. 3.43 times 10 to 24. Boom, buddy. Boom. Got that right. Spaceship approaches the planet. It loses gravitational potential energy and gains kinetic energy. This causes linear speed to increase. Ooh, okay. As the spaceship approaches the planet, gravitational force increase between them. This results in the planet pulling the spaceship closer to the planet. Increase in gravitational pull from the planet will cause an increase in the linear speed of the spaceship. Oh, okay. That's an E minor. Because I got the second, I said it like the second part of the or. Oh, you can't even see it, bro. What? My bad. Okay, yeah, that's an E minor because complete explanation with errors. I didn't, yeah, I said speed. I don't think I ever said linear speed. I guess that's a good one to make. T minus. So what's that? And then, I got the calc right. What would that be? That would give me, I had T minus 2UR. T minus 2UR. Okay, yeah, that's E7. Next question, next question. Oh, whoa, this question is super short. So 1160. What? Oh, no, yeah. Okay, so torque. See, this is where you get it right. Because torque for each rocket is only 580. 0.29 radians per second? Yeah, I was thinking that was wrong. Oh, yeah, you can use that equation. Correct angle conversion. Oh, okay, I gotta use it because I had this idea right here where this is equal to 2 pi. That's actually cool. Okay, at least I get a cheap take for that. Mass moves further away from center rotating, called rotational inertia take. Oh, I didn't say that. Okay, there is no outside torque, so angular momentum is conserved. L equals IW. Angular speed will decrease, causing period of rotation to increase. I'm just gonna check. Wait. Oh, C. I missed C. My bad. The rocket emits gas. Total mass of spaceship decrease. This will cause rotational inertia to decrease. Torque is constant, so angular acceleration will gradually increase. I just said gradually, but I did use the equation, so I guess it does count. This is the delta symbol. Okay. Let me see this. Yep, can. Okay, so I got the 14.6 right. I don't think I said mass moves further away. I think I get an E minor for this just cause I need to state mass moves further away. I kind of assumed it. Like I never stated it, which is my error. That's my error right there. That's still what, T minor 1R 2U. This is a U, bro. What is this handwriting right here? See, 1R 2U. Yeah, same for this one. So we get 7. Direction of restoring force does not change, or direction of restoring force remains down. Restoring force increases as she moves away from. Restoring force will negatively increase. Equation. Yeah, I use equation as explanation. Direction of restoring force does not change. I don't know if I stated that right then. I think I used the equation, so I think it might be fine. I'm not sure though. That one's a bit of an iffy one. Oh. Okay, so for B, I do not know what I'm doing. I am ripping. Yeah, they use phases. What about what's a non-phaser? Okay, tip here, hot tip, use phaser. Or use this equation, which I was going to use, but I never did. Yeah. That's my mistake. At least I got this one right. Oh, it's the wrong goddamn way, guys. How have I done that? Vmax equals to omega alpha. Okay, where have they whipped this equation out of? Hey, we got the last question right. I got another E minus tick. Just because I didn't say two supporting assumptions, like, what? And then I don't know if I get the other one right. It's like half. That's probably a U tick right there. There's a 2U, 1 excellent. I don't know what that would even give me. I think it's a point system. So I was short of points. Yeah. Oh, E minus and E only applies to E78 decision. Okay. So I got 3, 5. So it's M5. Wait, is it? I didn't get any merit? Oh my god. We're getting a 5 here. We get 7 plus 7 plus 5. 19 out of 24 right there. I'm actually quite happy with that for mechanics. This is my worst paper, so we look down here. E7. Wait, you can't even see it. What? Oh, it's because I put my screen like that. I couldn't even see half of it then. Oh well, I got E7. E7's a 19 here. 2017. Mechanics done. 2017 mechanics speedrun done. 44 minutes, 30 seconds. Pretty decent in my opinion. I could have been quicker though. I think if I can get sub 30s, that's where I'm looking at. That's what I need. Alright. Latest.